Today, we're going to talk about the very foundations of CAD, solid modeling. And there's no better person around to help tell that story than Phil Nanson, who's the manager of Parasolid components at Siemens. Phil, thanks for joining us.
Hi.
Shapr3D is using Parasolid, but many CAD systems in the world are using Parasolid. A lot of people characterize it as the de facto standard. And it's been around quite a while, and you see the name everywhere. And you and I know this because we've been on the development side of CAD, but a lot of our end users may not understand the importance of Parasolid and a kernel modeler. I was wondering if you could help them to understand what it is.
Essentially, Parasolid provides the core modeling engine for most of the CAD, CAM, and CAE applications that run on top. And our aim is to provide always a very broad, robust set of functionality that can work in a huge range of workflows. So guaranteeing that models will just work all the time, and also that you can get similar modeling and data compatibility between a very wide range of systems.
Our CEO Istvan Chinati has a collection of swords and was a champion fencer when he was younger. You go back to our first vlog, he talks about that a little bit. Yeah. And in our conversations leading up to the vlog, we learned that you have some experience with this kind of weaponry as well. Maybe share some.
Yes, I also fenced at school, though from the sound of it to nothing like the same level. And my alternate career was going to be as an armourer, making swords and medieval armour. And so after the diploma, I went off and trained for a year under someone to learn how to do it. I then concluded that I didn't have enough money, so I joined Shape for 18 months, at the end of which I concluded I did have enough money to go off and fulfill my dream of being an armourer. 18 months later, I had the same number in my bank balance, but a different sign, and concluded that actually I quite enjoyed working on CAD and it was time to return to that. And I've stuck with CAD ever since.
Now, you and I kind of go back a long way in our careers. And in fact, I was thinking back when you were starting at Parasolid, and we don't need to say the year, but it was a while ago.
Yeah.
At that time in Cambridge, UK, I was in Cypress, California, and I was a QA engineer at Unigraphics, finding bugs. And I might have sent bugs over to you that I found with the solid modeler. It's been a while.
I might even still have a green piece of paper with your name on it somewhere.
How did you end up here? What kind of other roles did you have as you made your way into the Parasolid team?
I studied at Cambridge and I did the maths followed by the diploma in computer science. And that involved doing a dissertation. And one of my friends had already started working for what was then Shape Data. Her descriptions of her work were really interesting. So I thought I could do my dissertation on that, and dug out Ian Braid's thesis and set off to write myself a basic planar solid modeler, which was basically fine apart from one critical flaw. As a pure mathematician, I considered such details as a UI or graphics irrelevant and just coded it pure, which did not lead to the best debugging experience in the world, it must be said.
At Shapr3D, we believe in the importance of a user interface as well. And if you think about the impact Parasolid has had on the industry, it's been, as we said, the CAD industry, depending how you count it, goes 30 to 40 years back. And the innovation of solid modeling was something quite big in the 80s. And maybe you could share with us a little bit about how Parasolid played a role in that history and some of the technologies that came before.
Parasolid, the level of robustness we provided was critical to Unigraphics' success with feature modeling. The robustness and consistency of operations became even more important at the point you had features. I like to think it was a very major factor in the success of the appearance of the mid-range modelers.
And if I go back to my early days in CAD, I'm going to call it 1985-ish, when I was first using an older version of Unigraphics. We didn't even have solid modeling then. For me, it was taking a profile and rotating it 360 degrees so it looked like a solid. At what point did commercial CAD systems start to have a level of solid modeling that was useful for people?
That point in the late 80s, is the point where solid modeling achieves sufficient functionality to be broadly applicable.
Okay. So, thinking back to those days, did you and the team, did you ever think that Parasolid would become so prolific in the industry? I mean, it's literally in hundreds. I don't know what the number is, but there's so many different tools that use Parasolid, and so much data today in the world is created with Parasolid. Was that the dream, or was that something that was thought possible?
That certainly was the original dream, even back before Parasolid, was to provide a solid modeling to the world. And I think the fact the decision was taken by, I think we were EDS at the time, to resume selling Parasolid more widely externally, I think that message of openness and that behavior of openness has enabled that original dream to be substantially fulfilled.
Yeah, actually, and I think that was a very that was driven by one person. I mean, Chuck Grindstaff was the guy that really drove the openness and brought that strategy to market. It was actually pretty cool to be a part of that back in those days.
Yeah, I think it was a remarkable decision, but I think it was a very good decision. But I could see how many people would have been dubious at the time.
It was not without controversy, that's for sure. From a technology perspective, what do you think were some of the key top few technologies back then that made it such a prolific product, something that people were jumping into?
Beyond just producing robust and generally applicable software, there's a lot you have to do to make the experience of using a component easy and safe for your customers, so that you can upgrade smoothly. Developed easy record and replay mechanisms so submitting bugs was efficient, and that we could add all bugs to our auto tests, and so we would guarantee not to get regressions. All these things reduced the cost of ownership of Parasolid. It wasn't the case that if you got a new version with a bug fix in, you had to rewrite 5,000 lines of code because the interface had changed. The other factor, which I think helped a lot, is because we got some quite different customers among our early adopters, we were forced to case harden and generalize our functionality very effectively and very early. And that meant it was a wider set of workflows than if we'd just been driven by a single customer.
I'm thinking back of during those days, I was an application engineer giving demos, and there were two things that we always had to demonstrate. And one of them was the different multiple types of blends, three-phase blends, and blending, diminishing, all kinds of crazy stuff. And the other was surfacing. Can you talk a little bit about those, and how quickly did those have to progress to make this battle hardened?
Range and of requirements on blending expanded hugely at that time, both in terms of configurations you can handle and, as you said, the shapes and style of blend that we had to support. A particular major change at that time was the introduction of face-face blending, so the ability to blend between different sheet bodies.
What was driving the change? Was it just because people were creating more complex parts in the case of automotive, or were they creating parts that were of the same complexity, but they just wanted to represent them in a more exact way for manufacturing?
You very much see the two drivers going on. Essentially, my guideline is, if you solve the new configuration, everyone's happy for 6 months, then they want it to be faster. And then 6 months later, they want it even more complex. And we spent a lot of time there. But also another particular driver was this desire for better accuracy in the model. I worked through the transition where initially people were designing their models with the blends just written on as annotations.
Yeah.
Left to the machine shop.
Mm-hmm.
And then they decided, no, they actually wanted to represent the blends in the solid. And that led to a host of problems where you suddenly realized that the blend you'd written on the drawing couldn't actually fit in reality. And we had to work through that and explain that to customers and so on, and work out what the desired solution in the area where the theoretical definition didn't fit was.
And these days, it's the plastic from the 3D printers now, which introduces a whole new set of modeling challenges and opportunities.
Oh yes, there are some fun problems around at the moment.
Could you share a few of those that are coming out as a result of this?
And people are basically trying to make and manufacture shapes they never could make and manufacture before.
Yeah.
So we're seeing a lot of shapes for which, while you can represent them with NURBS, it's not natural. You end up with an arbitrary grid of patches that don't actually contain any design intent.
Maybe this is a good segue to talk about convergent modeling. So as I mentioned, our last episode of the vlog series was with Ken Verspril, and we dug into the history of NURBS, which was crazy fun. And at least for nerds like us that like this stuff, but it was crazy fun talking about NURBS. And I asked him about the future of surface modeling, and he also mentioned this convergent modeling and representing objects with NURBS at the same time. Do you see this as something that will coexist in models? Is it eventually, do you think we're going to move more towards the faceted representations, or what's your view of the future for that?
I think they should coexist. A lot of the data has a natural representation which contains its design intent, and which frequently is the most efficient to represent it. You know, to take a simple example, if you're trying to represent through bolt hole between two mating surfaces, remembering that's a cylinder between two planes makes your model a couple of orders of magnitude lighter in data size, makes all your calculations vastly more efficient. The model that originally persuaded me of this was a cutting guide for knee surgery, where the interior is the shape of someone's knee, and the exterior is basically a blended block with holes and slots in. And so you're looking at one side of the part and going, this is a classic feature modeling or direct editing problem on analytic surfaces. And on the other side, you've got this hideous, bumpy, arthritic knee. And just go, okay, no, actually, I really want a model that has both those in there in order to be able to do this efficiently. And at that point, I became convinced that this was a technology we had to invest in.
We talk about convergent modeling being something that's relatively new. Are there any other really cool technologies in the last couple of years that you think our audience should know about?
The change in shapes is one major thing. The change in platforms is another, in cloud and mobile devices. 10 years back, that didn't exist. The idea you could use CAD in either of those scenarios would have seemed very far-fetched.
Yeah, and obviously we were super excited when the Parasolid team made the decision to move to iOS for the iPad, which I think was around 2015, and became one of the foundation components for Shapr3D. But the thought of running Parasolid on an iPad, I mean, you and I have been around a while, and I was talking with Ken Verspril about loading up a truck full of equipment to do a 1-hour demo, and the logistics involved. It's changed so much. So I think the hardware and distribution of the CAD software is really important.
Yeah, and the spread in the range of people who could, it's the phrase "the democratization of CAD" has been around for probably as long as I've been in the industry.
No, that's great. So we're pretty close to the end, and I want to thank you for joining us again, Phil. I mean, this whole history of CAD is really pivoting around Parasolid, solid modeling, making that ubiquitous across the industry. Congratulations on a wonderful career and delivering this technology to the market. And thanks for joining us today.
Thank you. It's been good fun.
You can edit imported mesh models in Shapr3D using any of the Boolean operations: subtract, intersect, or union. You can only use these operations with imported models. They won't work with incomplete mesh sheets or mesh scans. However, you can still import these mesh objects as a reference for designing new models. Thanks for tuning in to our Shapr3D Tip of the Month. If you're looking for more tips and tricks like this, check out our library of tutorials and webinar recordings, and make sure to subscribe to our channel for upcoming content.